So of course registers are much more faster than the main memory. So since the maps always only work on the registers, it is much more faster than the instructions in the instructions like 8086. You can, for example, add one number and one register. Let me write one example here for you. In 8086, we have some general purpose registers or X, and the X each one has 16-bit capacity. So you can write an instruction like this at X and number. But this is a Cisco instruction complex. Instruction set. Computer. In the 1886 assembly. The first one is the destination, so AX and number will be added together and the result will be right back in AX or accumulator. So as you can see this instruction in the CISC, you can have one operand that is from the memory and another that is from registers. And reading data from the memory is very time-consuming operation. But in the MIPS assembly, all of the data are inside the registers. So all of the mathematical operations, logical operations will be performed over the data that are inside the registers, and the registers are much more faster than the random access memory. So of course, when you want to perform operation first you have to read them from the memory and store them in some temporary registers. So operating on memory data requires load and store. So in order to make the execution of the program faster, the compiler should use registers for the variables as much as possible. We have 32 registers, so we can save the data one time and store them into the registers and then perform all of the operations over them. Instead of always going to the memory and read data from the memory like something that we have to perform in 8086 assembly in the MIPS. Since we have a lot of registers, we can easily sort all of the most frequently used variables inside that registers and then access that data by using that register. Another way to provide the operands for an instruction is using immediate data. For example, we want to add a constant value to the content of one register. So it is possible to put a constant value here and the instruction that is support this type of the operand as different opcode add immediate. This I in the opcode means that there are one operand in the format of the immediate data, so the content of the $sign is 3 and the value 4 will be add together and the result as back into $sign as 3. So we add 4 units to the content of the registered $sign as 3. We don't have to subtract I as you by 4 instead of that 1, you can use a negative number here. So add immediate with negative number means that you want to perform subtraction. Another design principle that follows by the inventor of the MFS is make the common case fast. Small constants are common, so immediate operand avoids a load in instruction. This is the reason that they provide immediate auto racing mode or immediate instruction set that it avoids load instruction. Instead of loading this constant number from the memory, you can easily put them as a one of the operands of the instruction. There is a special register in the MIPS register 04$90, which is also can be used by this format $0. And this register always contain a constant value 0 and you cannot change it or it cannot be overwritten. It is hardwired to the 0 or ground, so this register always holds number 0. So you cannot store any number or variables here. Why we use it? For example, if you want to transfer the content of one register to another one, there isn't any move in instruction. Instead of that one, you can use this formula. I want to get a copy of C1 and put it in T2. For example, there isn't any assignment operation in the MIPS. Instead of that one, we can mention in this way at the $sign as 0 with register 0. This is always 0. So the 0 and this one will be add together. So the answer will be S1 and the S1 will be a store in PT2. So a copy of S1 is moved into the PT2. So this is the way that we perform assignment. Okay. Let's review some basic information about the binary numbers. Unsound binary integers assume that we have an AND number. So as you know, for example, 1, 0, 1, 1. This one has 2 power 0 significant 2 power 1, 2, power 2, and 2 power 3 and this x0 x1. This is x0. And this is 2 power 0 2. Power 0. 2 power 1 to power 2 to power 3. So in order to convert it back to the decimal notation, you should add them. This is 1, 2, 4, 8. So 8 plus 2 plus 1 is 11. So this is number 11. In the small. So an infinite number ranged from 0 to 2 power n minus 1. In this example, n is 4, 2 power 4 is 4, 16 minus 1 is 15. So by 4-bit number, you can display a number between 0 to 15 by 8. You can display a number between 0 to 255 because 2 power 8 is 256 minus 1 is 255. Core 10-bit. You can display a number between 0 to 1023. What about is 32-bit number? It will be ranged between 0 to 4 billion something. This is for unsigned binary integers, so it will be on the positive but in the 2's complement sign. Integers. As you know, in order to display sign integers in 2's complement format, the leftmost bit will be considered as the sign bit. If it is 0, then the number is positive. If it is 1, then the number is negative. So an AND bit number in 2's complement sign integer will be range in -2 power n minus 1 to plus or positive 2 power n minus 1. Minus 1. Let me give you an example. In the unsigned format, this value is 0 and the last one is 15, but in the same format, from this point, the number will be negative. So these numbers are negative and these number are positive. So the positive part is the same. So this is 0, 1, 2 till 7. And for this part, how can I find out which number is stored in this part? For example, for this number, what is the equivalent? For the positive one, we say that the first bit magnification is to power 0, to power 1, to power 2, to power 3. What about here for this one? The last bit has -2 power. It. So it is 1 from I write it from the right side 1 times 2 power 0 to power 0 is 1 plus. This next one is 1 again, 1 times 2 power 1 or 2 plus 1 times 2. Power 2 or 1 times 4. But the last one is 1 times 2 minus 2 power 3 or minus 8. So if you add these numbers minus 8 plus 4 plus 2 plus 1, it will be minus 1. As you can see, the most significant bit has minus magnitude here, minus x index and minus 1 times 2 power n minus 1. So this is -1. This is -2. -3, -4, -5, -6, -7. And this is the -8. So, here for 4 beats, I have numbers between -8 to +7 according to this formula, -2 power for -1 it is 2 power 3. So -8 to 2 instead of input 4 to power 4. Mine is to power 3 or 8. -1 is 7. So the range will be between -8 to +7 for the 8 beat. In positive, as I mentioned, it will be between 0 to 255. For the negative, it will be between -128 to +127. And for the 32 bits, it will be between -2 billions to +2 billion. So as I mentioned, the most significant bit in 2's complements assigned integers is the sign beat. In the MIPS we have 32-bit numbers. So the beat 31, the leftmost bit is sign beat, and for negative it is 1. For positive it is 0. Of course, we cannot display this number by in beats. Non-negative numbers have the same unsigned and 2's complement representation. Of course. Let's hear the most positive number that you can display, of course, can be constructed in this format. Put all of the beats 1 only the sign which should be 0. And for the negative, the most largest negative number that you can, or as small as actually number negative number that you can have is, by this way put all of the number 0 and the sign with 1. In my example, -8 is the smallest number. The next point is sign extension. For the sign's value, when you want to increase the number of beads, you cannot put 0 in the left side. For example, this is number 1 in 4-bit. If I want to represent 1 in 8-bit, it can be easily constructed, but put in 40 in the left side. By this way, you can extend your number to any number of beats. For beats 8 beats, 1232 beats. You can't put some 0 for the positive numbers, but for the negative number, it is not in this way. For example, this is -1, as I mentioned here. So if you want to extend it into the 8 beats, this is -1 in 4 bits. If I put 0000 and then put this number, then the number become positive because the leftmost bit is the sign beat, and this is not anymore -1. Instead of adding 0, you should add the sign beat for negative number 1, for positive numbers 0. So in order to create an 8-bit -1, I should add 1 here. And then, with this number in this part. So this is the sign extension. For any other negative number, this is correct. For example, this is -8. And this is -8 in 8-bit. Or in 16-bit. So as you can see, I put 12 here in order to extend this 4-bit number into 16-bit number because it's a negative number. I should use this sign beat and put it here. You can easily check these numbers that are correctly. All of them are -8.